Hey everyone, welcome back to the Physics Past Paper Series. Today we're going to talk about the CIE 9702 variant 4143 from the May-June 2024 series. All right, so let's see the first question. Define gravitational potential at a point. Now, to answer this, just wanted to reintroduce to you our grade booster packs, which we have introduced in the recent videos, but this is your chance to see them in action, what they're going to help you out with. So it's basically syllabus points, the relevant questions that you will frequently encounter in the past papers, their answers, their modeled answers aligned with the marking schemes, and on the right hand side, the years. So the years over here will show you how frequently you're likely to encounter these while practicing the past papers. So most of the students are able to do well on the numerical questions, calculations, formulae, but most of the students struggle with articulating their ideas together to to have a proper reasoning in their explanations. So this is for you to help you with that. Other things that we are offering, important derivations. So derivations also are somewhere around like 10%, less than 10% of every paper 4 paper exam, sorry. Uh, this doc has all the derivations which are listed in the syllabus, along with the few that are examined again and again. For example, these capacitor in series, capacitor in parallel, and other kinds of also. This is like a frequently examined derivation also. Definitions and formulae, basically it's a rundown of all the major terms, major formulae, all everything that you need to, And last but not the least, the graphs. Every student struggles with the gravitational potential and the field graphs, especially the electric field potential graphs between opposite charges and the like charges. So for that, we have got you covered. All you have to do is to go through them. You can see the functions written over here. You can see the shapes of the graphs. And hopefully this will be enough for you to figure out how to sketch these types of graphs. So you can find these on our Patreon page. This is available. You can download this. The link will be in the description below the video. So hopefully you will like this thing. All right, so let's see. Define gravitational potential at a point. So just to show you a demo of what the frequently examined questions can do for you. Define gravitational potential at a point. This is a very frequently, as you can see, frequently examined question. It is the work done per unit mass and moving a mass from infinity to that point. So, gravitational potential at a point in gravitational field is the work done per unit mass to bring the mass closer from infinity to that point. All right. Satellite X of mass m orbits a planet at a constant distance 4r. This is your planet, satellite X. From the center of the planet, this is the planet over here. Second satellite Y, which is this one, of mass 2m, orbits the planet with the orbital radius r. Gravitational potential at x due to the planet is at x due to the planet is minus phi. The planet is a uniform sphere. So we know that the general form of the gravitational potential is minus Gm over r, where r is the center to center distance, mass is of the source. Okay. Now, explain why the gravitational potential at x is negative. Okay, so first we answer this. There are 2 points to this. Again, you will see this over here. Explain why the gravitational potential is negative. Because it's defined as 0 at infinity, and since gravity is an attractive force, work is done by the field to move a mass from infinity to any point closer. So, potential at infinity is defined as 0, and work is done by gravity or gravitational force to bring the mass closer. Therefore, resulting in negative potential. Okay, state an expression in terms of phi for the gravitational potential at y due to the planet. Okay, so we know the general formula of potential, that is minus Gm over r. M is the mass of the source of the field. In this case, that would be the mass of the planet, not the satellite. They haven't given us any mass of the planet over here, so we can rewrite it as mp. So for x, phi x, they have written it as minus phi, and that would be minus Gm, mass of the planet, divided by 4r. Now for phi, phi y, you will have minus G, mass of the planet, divided by r. Now, how to make it in terms of this? You multiply 4 over here times by 4 over here, and notice that this thing has now become minus 5. So this is 4 minus 4, 5. So minus 4, 5. Complete table 1.1 by giving expressions in terms of sum or all of m, r, and phi for the quantities indicated for each of the satellites x and y. Okay, so one of the problems over here is that we do not have m, mass of the planet, and they're not saying that we can use mass of the planet or g. So that means for g and p, g and mass of the planet, we need to rewrite it in terms of phi. So let's take this over here. So GMP would be 4R5. Simply just cross multiplication over here. So whenever we encounter GMP, we will use that. So gravitational field strength at X, we know that would be GMP over 4R whole squared. So this is like doing GMP. So GMP, we just wrote it as 4R5, 4R5. Over here you have 4R squared. So one of the 4R's will get canceled. So you have phi over 4R. Okay. Now the satellite Y, same thing. You have GMP over R squared. So GMP, we wrote it as 4R5, 4R5 you have r squared. So r and r get cancelled. So you have 4 phi over r. Okay, now gravitational potential energy of the satellite. So EP is mass times, so for x is mass times by phi of x. So that would be mass times by minus phi. This would be mass m of satellite. So minus m phi simply. Okay. Similarly for y, you have also the same thing, 2m, because satellite y was twice the mass of x. So 2m and minus 5y, which we wrote it as minus 4 phi. So this becomes minus 8m phi. So minus 8m phi. And that's your first question. All right, moving on to the second question. State the magnitude and the unit of absolute zero on the thermodynamic scale. This is easy. This is simply 0 Kelvin, or you can write it as 0 Kelvin. Explain why the temperature measured using a laboratory liquid and glass thermometer does not give a measurement of thermodynamic temperature. So thermodynamic temperature is based on the ideal properties, ideal gases, ideal properties. However, it's a theoretical scale. Liquid and glass thermometer is based on the empirical scale, something that you can measure from the changes of thermometric properties. So for measurement through thermometer relies on uh, changes in thermometric properties of liquid. So it does not, for thermodynamic scale, does not require that. Figure 2.1 shows a simplified diagram of a type of thermometer called the platinum resistance thermometer. So you have platinum wire, plastic strip, large glass tube. Glass tube is immersed in an environment in which the temperature is to be determined. Resistance between the terminals X and Y is measured. Shows the variation of resistivity rho of platinum with thermodynamic temperature T. All right. Explain how figure 2.2 shows that the platinum is a suitable metal for use in a resistance thermometer. So one thing you can see over here is that this has a linear graph over here. That means a constant change over here, constant monotonic increase of rho with temperature, thermodynamic temperature. Okay, so that's all we just need to write over here. Because graph is linear, showing constant monotonic. Monotonic means either it increases or decreases. So monotonically increasing, constant monotonically, constant, sorry, constant and monotonic increasing of rho with T. All right. Suggest a reason why platinum resistance thermometer is not suitable for measuring a rapidly changing temperature. So rapidly changing temperature, uh, we just need to suggest it. So for rapidly changing is this responsiveness. Okay. So responsiveness is actually determined or governed by specific heat capacity. So if the specific heat capacity is low, the thermometer will be responsive. So that's what we just need. So um, high specific heat capacity, sorry, heat capacity of the thermometer can be a reason for unsuitability. Okay, suggest a type of thermometer that is responsive, that is suitable for measuring a rapidly changing temperature. This is easy. Thermocouple. Thermocouple is very responsive. The negative temperature coefficient thermistor may be used as a type of resistance thermometer. State one way in which variation of temperature of the resistance of a thermistor varies with that of a platinum wire. So as it says, negative temperature coefficient. So basically, the resistance will decrease with temperature. So temp resistance of thermistor decreases with increase in temperature. All right, that's it. Question number 3. State what is meant by an ideal gas. Okay, so let's see the definition over here. Uh, an ideal gas is a gas for which the product of pressure and volume is directly proportional to its the absolute thermodynamic temperature. So if we write the formula, we have to identify the variables of it, especially the temperature. So temperature has to be identified as absolute thermodynamic temperature, or at least thermodynamic temperature. So a gas which obeys, there's another definition also, PV over T is constant, where P, V, and T, you can define that, where P is pressure, V is volume, and T is absolute thermodynamic temperature. You could also have an all. You could also sorry. You could also do the same thing with PV proportional to T instead of this thing. So PV proportional to T also. Same thing. All right. Use one of the basic assumptions of kinetic theory to explain what can be deduced about the potential energy associated with random motion of the molecules in an ideal gas. So, uh, potential energy is related to intermolecular forces. Since there are no intermolecular forces in ideal gases, so no potential energy. So ideal gases, ideal gas molecules have no intermolecular forces so potential energy of is zero. This is also written in the FAQs over here. So somewhere over here, I think you can see that. Okay, this one, the last one. Potential energy between the atoms of an ideal gas is that gas molecules are assumed to be point masses with no size, no intermolecular forces. Assumption leads to conclusion that potential energy between the molecules is negligible. That's it. A sample of 0.26 meter cube of an ideal gas is at a pressure of this and a temperature this. Determine the number of molecules of the gas. So over here we will use the equation of state. So PV is equal to nKT, where K is the Boltzmann constant. So N would be PV over KT. So pressure is given as 2 10 raised to power 5. Volume is given as 0.26 meter cubed. Temperature is given as 290. We just need the Boltzmann constant. The Boltzmann constant, you can find the value from this 1.38 10 raised to power minus 23. Oh, sorry. 1.38 10 raised to power minus 23. So 2 times by 0.26 divided by 290 divided by 1.38 times by 10 raised to power 5 plus 23. We get this value 1.299, roughly 1.3, 10 raised to power 25, so 1.3, 10 raised to power 25. The average translational kinetic energy of one molecule of the gas, this is also easy. The formula is 3 by 2 kT. So that's all we have to do, 3 by 2. K is 1.38, 10 raised to power minus 23. Temperature is 290. So 3 times by 1.38 times by 290 divided by 2 times by 10 raised to power minus 23. You get 6.003 or 6 10 raised to power minus 21. So 6 10 raised to power minus 21. The internal energy of the gas. Explain your reason. So internal energy of gas, of ideal gas, is equal to net kinetic energy of molecules. So that would be simply N times by Ek. So number of molecules is 1.3, 10 raised to power 25, times by 6, 10 raised to power minus 21. So answer, sorry, times by 1.3, 10 raised to power 25. We get this value. So 78039 joules. So you can rewrite it in standard form also, or 78,000 also will be fine. All right. The volume V of the gas in B is now varied, keeping its pressure constant. So isobaric basically. On figure 3.1, sketch the variation with V of the internal energy of the gas. Now, for this, you need to understand that net U of the ideal energy of the gas, we just said that that is N times by Ek, which is 3 by 2 nkt. Nkt is also equal to PV, so that means this is also equal to 3 by 2 PV. Pressure is constant over here this time, so that means that U is directly proportional to volume. So this would mean straight line passing through the origin, uh, sorry, so passing through the origin. That's it. All right, moving on to the next question. State what is meant by resonance. Okay, so similarly over here, we know the definition of resonance, that's the maximum amplitude when the driving frequency is equal to the natural frequency of the system. So let's see this definition over here just to show you that we have it over here. Uh, yeah, state what is meant by resonance. Force frequency of an oscillating body matches its natural frequency of vibration, resulting in a maximum amplitude of vibration of the oscillating body. So that's what we need. So resonance is the oscillations at maximum amplitude caused by driving frequency becoming, equal to natural frequency of the system. Now, you might think that I'm showing you different definitions over here and writing different definitions over here, so I'm just giving you options over here. So this is the main content over here. Obviously, we have limited space, so you can change your wordings a little bit, simplify it, and obviously you will have multiple options for answering this. Okay, a small ball is held in a place using a stretched spring. One end of the spring is fixed to a wall and the other end is attached to a vibration generator. Okay. Initially, the vibration generator is switched off. The student displaces the ball vertically and then releases it. Figure 4.2 shows the variation of displacement of the ball with time after it is released. State the name of the phenomenon illustrated by the decrease in amplitude of the oscillation. So this is easy. This is called damping. And specifically, this would be light damping. Light damping. Explain the decrease with time of the amplitude. So how do we explain it? It's basically due to the resistive forces acting on the ball. Oscillations will lose energy. So amplitude decreases gradually due to loss of energy. You could say due to gradual loss of energy also. Gradual loss of energy from the system due to resistive forces acting on the ball. That's it. Determine the frequency of oscillations of the ball, so we can see that from the time period. So for that, we just need to look at the maxima maxima or minima over here. So where the maxima occurs, where the minima occurs over here. Okay, or where the 0 points are basically. So let's see over here. Let's take an easy point over here. This is a minimum point. This is a minimum point. So this is 0.25. This is 0.5. So the distance or the time difference is 0.25. So 0.25 seconds is the time period. So frequency is 1 over time period. So 1 over 0.25 seconds. So 1 divided by 0.25, that is 4 hertz. Now, vibration generator in B is switched on, and its frequency f of vibration is gradually increased from 0 to 10 hertz. On figure 4.3, sketch the variation with f of the amplitude of the oscillations of the ball. Okay, so one thing you need to remember over here that there is a light damping already over here. So if there is a light damping on the system, the resonance will not become infinite over here. The amplitude does not become infinite. So due to that light damping, it will curve back. And where it's curving? At 4. So we need to draw a line at 4. So 4 divided 4 divided by 0.25, that is 16. So 10. So 4 is at 16. That means this is the point over here. So this is your 4 over here because 2.5 is divided over 10 markings, so 0.25, 4 divided by that, 16. So 16 marks after 0. So it will go like this and like this. That's it. All right. Moving on to the next question. Define electric field. So just like gravitational field, electric field is the force per unit charge. So let's see this over here. So electric field, define electric field, electric field. This is the alternate definition for strength also. So you can like not write strength. It's the force experienced by a unit positive test charge placed in the electric field. Or that's it. So vector, obviously this is a vector quantity also. So force per unit positive charge. That's it. Okay. Figure 5.1 shows two parallel conducting plates that are in vacuum. The plates are separated by a distance of 6.7 centimeter and the potential difference PD of 430 volts between them. On figure 5.1, draw 4 field lines to represent the electric field between the plates. So this is positive to negative. This, so copy. Okay, nope. Never mind. Oh, sorry, no. So equidistant as best as possible because electric field in between two plates is usually uniform. So roughly about the same distance from each other. Okay. Determine the strength E of the electric field between the plates. So that is just the formula is V over D, potential difference divided by the distance between them. So that is 430 divided by distances should be in meters. So 6.7, 10 raised to power minus 2. So 430 divided by 6.7 times by 100, you get 6417. So basically 6400. An electron travels at a speed of 2.6 10 raised to power 7 meter per second towards the region between the plates as shown in figure 5.1. On figure 5.1, draw the path of electron as it moves between and beyond the plates. So, okay. So it will only experience any acceleration or change in direction as long as it's in between the fields or inside the, after that it will just keep on going straight. So it will curve a little bit and after that straight. So that's the electron over here. A uniform magnetic field is now applied in the region of the electric field so that the electron in B travels undeviated through the region. Determine the direction of the uniform magnetic field. So as we can see this over here, uh, elect electric field is causing the electrons to go upward. This is your electric field, sorry, force due to electric field. So force due to magnetic field should be downwards. So this is electron, obviously opposite to the conventional current direction. We use Fleming's left hand rule over here. We need the force downwards. Current direction is this. So thumb direction will be into the page. Okay, so uh, it would be into the page. Okay. Explain with reference to the forces exerted by the two fields on the electron why the path of the electron is undeviated. So the reason is simple, that the uh, forces exerted by electric field, electric and magnetic fields are equal, uh, acting on the electron, sorry, acting on electron are equal but opposite, sorry, equal in magnitude but opposite in direction. Opposite in direction, resulting in no net force or acceleration or deflection. That's it. Determine the flux density B of the uniform magnetic field. Give a unit for your answer. So this is easy. We just said that the force due to electric field, that is QE, becomes equal to BQV. BQV is velocity. So let's rewrite U as velocity. U is velocity. Have they identified? Okay, no, they haven't. Okay. So we cancel out the Q and the Q. So B will just simply be E over U. E we have already found out, 6417.9. divided by speed is given as 2.6 10 raised to power 7. So answer divided by 2.6 10 raised to power 7. This becomes, uh, let's write it in the standard form over here, 2.468 or 2.5 basically, 10 raised to power minus 4. So this is roughly 2.5, 10 raised to power minus 4. So unit is Teslas over here. All right, moving on to the next question. Figure 6.1 shows a capacitor of capacitance C connected in series with the resistor of resistance R. Initially, the switch is open and there is a potential difference of 12 volt across the capacitor. At time t is equal to 0, switch is closed so that there is a current I in the resistor. Figure 6.2 shows the variation of I with t. Now, this is an exponential decay graph. Explain the shape of the line. So we have to not describe it, but explain it also. So a few things to notice over here. The potential difference across capacitor, that is the same. Potential difference across capacitor is same as potential difference across resistor. That means the current flowing through them also is the same. Secondly, potential difference across capacitor is given by Q over C, which basically means that this is proportional to the charge on the capacitor. Similarly, the current flowing through the resistor is, we know the rate of flow of charges, so either we can write it like this, or we can write it like this. Equally fine, which means that current is the rate of flow of charges, right? So what's happening over here is that capacitor is losing the charges. And as it loses the charges, the rate of decrease of charges also decreases. So that means the current itself would start to decrease. So as the charges are decreasing, rate R is also decreasing. So charge itself is proportional to this thing. So as charges are decreasing, the rate of decrease of charges also decreases. So what that further means is current would also have the same thing. So as current decreases, the rate of decrease of current would also decrease the same way. So the math of this is not in our scope, otherwise we could show this by calculus also. So we just have to write over here what we just wrote over here. So the potential difference across capacitor is equal to potential difference across resistor. All right. The charge on capacitor is proportional to potential difference across capacitor. So charge is decreasing and rate of decrease of charge also decreases. Therefore, as current decreases, rate of decrease of current also decreases. That's it. All right, moving on. Use figure 6.2 to determine the resistance R. So, okay, so we know that the initial potential difference was given as 12, and the initial current is given as, let's see, 0.01 is going to be the each small mark over here, so 0.11, 12, 13. So this is 0.13 milliamps. So as we said over here, the potential difference over the capacitor or across the resistor are the same. I naught is 0.13 milliamps. So therefore, R is equal to V naught over I naught, 12 divided by 0.13 10 raised to power minus 3. So 12 divided by 0.13 times by 1000, you get 9.231 10 raised to power 4 ohms. So you could just either write it as 9.2 10 raised to power 4 or 92,000. Or yeah, 92,000. Either way, it's fine over here. The time constant tau of the resistor. So time constant in figure 6.1, we need to figure that out. And we need to figure that out from the decay of the current. So we know that I is equal to I naught e raised to power minus t over tau. So that's what we need. We need an I after some time t. I naught we already know. So let's take, for example, 8 seconds over here. So this is 0.02 then. So that's what we need. So I is equal to I naught e raised to power minus t over tau. So we can take 8, 0.02. So after 8 seconds, you have 0.02. I naught was 0.13. E raised to power minus 8 over tau. So ln of 0.02 divided by 0.13 would be equal to minus 8 over tau. So time constant would be minus 8 over ln 0.02 divided by 0.13. So minus 8 divided by ln 0.02 divided by 0.13. So you get 4.274 seconds. So rounding up to two significant figures, so that is 4.3 seconds. Use your answers in B to determine the capacitance. C, time constant is equal to RC. C would be equal to time constant over R. time constant we found out to be 4.3, or we can use uh, slightly 274. Even 4.3 would be fine over here. R we found out to be 9.231, 10 raised to power 4. This is equally as fine as doing 4.3 divided by 92,000. Equally fine. The value would be very close to each other. So equals to divided by 90 to 9231, 0. So this value is giving us 4.63, 10 raised to power minus 5. Let's see what happens if we use 4.3. So 4.3 divided by 92,000, that gives us 4.67. So 4.6 is like fine. Let's go with 4.7. Let's use this one. So 4.7, 10 raised to power minus 5 farad. All right, on to the next question. A circuit contains a power supply that provides a sinusoidal alternating input voltage V in. There's an output voltage V out across a load resistor R. State the purpose of the circuit in 7.1. So basically what it's doing is it's converting AC voltage into DC pulsating voltage, not the DC smooth voltage, DC pulsating voltage. So it's basically doing the rectification over here. So state the purpose. So the arrangement, so the diodes are arranged to provide full wave rectification of input voltage resulting in a pulsating voltage in one direction. Okay. Figure 7.2 shows the variation of V out with time. So as you can see, this is a pulsating voltage. The load resistor R has a resistance of 370 ohms. Show that the maximum power dissipated in R is this. So maximum power comes from maximum voltage squared over R. So V naught, we need to know what V naught is. So 6, 7, 8, 9. So 9 volts, 9 squared, 370. So 81 divided by 370, that is 0.22. So if I convert it into normal mode, this would be 0.2189, so roughly 0.22 watt. On figure 7.3, sketch the variation with T of the power dissipated. So power is also dissipating the same way as the rectified voltage. And it would do the same way for the input voltage also, because it's a power, as you can see over here, this involves squaring of the voltage. So the signal would be in one direction also for the power, like for the power function. So what they've shown us is that period is 4. So 0.2, okay, all right. So power would be 0 at 0 0.2, 0 0.4, 0 0.6, 0 0.8, but maximum 0 0.22. This is 0 0.3, 0 0.2, somewhere over here. So this would be the points for this. So let's go. Oh, sorry. This is getting worse. 0, maximum, 0, maximum, 0. That's it. These are the maximum points, 0 0.22. That's it. Right. Calculate the mean power dissipated in hours. So mean power is given by the power naught divided by 2, maximum power divided by 2. So 0.22 divided by 2, which is 0.11, 0.11. The circuit of figure 7.1 is disconnected and R is directly connected across a power supply. Explain without calculation how the mean power now dissipated in R compares with the answer in B3. So that would be the same. So as we said before, let us show you the graph over here. The power, since it involves squaring of the voltage function, whether it's a rectified function or whether it's the original input alternating function, it would be the same. Power would uh, look the same. So look at this. So this is the original current, alternating current, half wave rectification removes one cycle, half cycle, sorry. In full wave rectification, half cycle is reversed, and power function remains the same whether or not it's the alternating current or the fully rectified current. So power function, or the power versus time, or the power function remains the same. So you can say power function remains the same or power time relationship remains the same. So power time relationship remains the same whether it's alternating voltage or fully rectified voltage. So mean power would remain the same. That's it. All right, state what is meant by a photon. So let's see the definition over here. Basically, it's a massless packet of, or massless quantum of electromagnetic energy. So let's see this over here. This is just to show you how this great booster pack is going to help you with this. So fundamental particle of electromagnetic radiation with zero mass, zero electric charge, carrying energy and momentum. Discrete packet of quantum of energy of electromagnetic radiation. Okay, So the reason why the first line is a little bit more detailed, because sometimes the question says explain what is meant by a photon. So when the question says explain what is meant by a photon, then you can write a little bit more detail into it. But if it just says state what is meant by a photon, then it's just a discrete packet or quantum of energy of electromagnetic radiation. That's it. So discrete, sorry, it is a discrete packet of electromagnetic, energy of electromagnetic radiation. Discrete packet of electromagnetic energy. That is also a fine definition. Okay, or energy of electromagnetic radiation also, same thing. All right. Figure 8.1 shows a tube in which X-rays are produced at the metal target. Particles are accelerated from the filament to the target by a constant high voltage applied across the terminals X and Y. Okay. State the name of the particles. Simple electrons. On figure 8.1, use plus and minus signs to label the terminals X and Y to indicate the polarity of the high voltage. So this is easy. This is going to be the positive charge. This is negative. So this is the anode. This is the cathode. All right. For an accelerating voltage of 32 kV, determine the maximum energy in mega electron volts of an X-ray photon produced at the target. Okay. So one few things you need to be have at fingertips now, that 1 electron volts equals 1.6 10 raised to the power minus 19 joules, and 1 mega electron volts similarly, that would be 10 raised to the power 6 added with this, multiplied with this, so that would become minus 13 joules. So how do we find out now? W is equal to QV. That would be the maximum energy. So charge on the electron is 1.6 10 raised to the power minus 19 coulombs times by accelerating voltage 32,000. This will give us the joule energy. So 1.6 times 10 raised to the power minus 19 times by 32,000. This is 5.12 10 raised to the power minus 15 joules. So 5.12 10 raised to the power minus 15 joules divided by 1.6 10 raised to the power minus 13 joules per mega electron volt. That gives us 1.6 10 raised to the power minus 13. That gives us 0.032. So 0.032 mega electron volts. The maximum momentum of an X-ray photon produced at the target. So to get that, we need the relationship between momentum and energy. So the relationship is momentum is equal to energy over speed. Just to show you, we have the derivation of this also. I think this is in over here. So momentum of a photon. So this definition is just simply momentum h over lambda, but this one with the energy, you can see the derivation over here. We're comparing this with E is equal to mc squared. So P is equal to momentum is equal to energy of the photon divided by C simply. So that's what we just simply need. P is equal to energy over speed of light. Sorry. So energy, we have calculated this in mega electron volts, but for this, we need this in joules. So 5.12 10 raised to power minus 15 divided by speed of light 3 10 raised to power 8. That's it. So 5 point, actually we already had that, didn't we? Yeah, okay. So divided by 3 10 raised to power 8, 1.7 10 raised to power minus 23. So that is your 1.7 10 raised to power minus 23 Newton second. So for Newton second, we have to use the joules. Minimum wavelength of X-rays produced at the target. So P is also equal to H over lambda. So lambda would be H over P. So H is Planck's constant, 6.63, 10 raised to power minus 34. These constants should be on your fingertips by now, so you should just start memorizing them. Momentum is 1.7, 10 raised to power minus 23, so equals 6.63, 10 raised to power minus 34, divided by answer, you get 3.88. 5 10 raised to power minus 11, so roughly 3.9 10 raised to power minus 11. Explain why X-rays can be used to produce images of internal body structures that have good contrast. So only way we can have a good contrast from the X-rays is if the body structures have huge differences in attenuation, linear attenuation coefficients. So I think we also covered this in FAQs also. Let me just just go through it. I think if I show you this over here, um, let's hope it is. Let's hope it is. X-rays, X-rays. No, I thought we did. Okay, anyways, never mind. This is an easy thing over here. So all we need is to have good contrast. So bone, so uh, we can say that bones and surrounding soft tissues have high differences in their linear attenuation factors, sorry, coefficients. Bones can absorb, attenuate X-rays to a greater degree than soft tissues. Therefore, the resulting scans, therefore the transmitted intensities will be different or will have differences will have huge differences resulting in good contrast. That's it. All right, on to the next question. Define half-life of isotope, radioactive isotope. Okay, so just to show you again, we have this covered over here. Sorry, find radioactive half-life, time required for half of the radioactive nuclei in a sample to undergo radioactive decay. Okay, so time required, sorry, by half of the radioactive nuclei in a sample to undergo radioactive decay. Radioactive isotope decays to radioisotope Y. Sample contains only nuclei of X at time t is equal to 0. Figure 9.1 shows the variation with T of the numbers of nuclei of X and of Y as the sample decays. State the name of quantity represented by the magnitude of the gradient of the line X in 9.1. So the gradient dN over dt is basically activity. So activity. Okay. State three conclusions about X and Y that may be drawn from figure 9.1. Conclusions may be qualitative or quantitative. Use the space below for any working that you need. Okay, all right. So a few things to notice over here is that the number of nuclei at every time from 0 to 60 seconds, that remains the same. So over at t is equal to 0, it's 4 times 10 raised to power 2, 2. Over here, it's 2 plus 2, because both of these have 2 plus 2. Similarly, over here, somewhere over here, these two numbers, when you add them up, this will equal to 4 plus 4, basically. This and this also, when you add them together, you will equal 4. So total number of nuclei remains constant. Total number of nuclei remains constant. Second thing, we know from the same observation, we know that X is radioactive, but if the total number of nuclei remains the same at all times, that means Y is stable. Because if Y itself was radioactive, we would see a decrease in nuclei also. Like the rate of increase of nuclei would also decrease. So Y is a stable isotope. Y is a stable isotope. Similarly, over here, since total nuclei are the same, the Y is a stable isotope, we can comment on the half-life also. So half-life, anything we can comment on, anything that we can draw a conclusion for. So we could comment on the half-life. And what's connected with half-life? We have decay constant, lambda. So lambda is equal to ln2 over half-life. We can also comment on activity because they have already asked us about it. So you can comment on the activity also. But you would have to take the gradient of the graph over here. Half-life is easy to figure out. So if you have 4 over here to get to 2, oh, sorry. So for 2, you have somewhere over here. So this is 15. This is 13.5. Roughly 13.5. So half-life of X is approximately 13.5 seconds. Yeah, all right. The mass of the radioactive isotope in sample B is 7.3 10 raised to the power minus 4 kg at time t is equal to 0. Determine the nucleon number of isotope X. Okay, so we can deduce that from the number of the moles. So if we can figure out the number of moles of isotope X at the start, we can compare that with the mass relationship. So we have two relationships over here: number of particles over Avogadro's constant and mass over molar mass. So molar mass is basically on the nucleon number over here. So molar mass is the nucleon number or the mass number in grams. So that's what we are actually trying to find out. So where n is number of particles at t is equal to 0, n is moles of X, t is equal to 0, m is molar mass, and m is mass of X. Okay, so all we have to do is to rearrange this. So we have m times by Avogadro's constant divided by n. So mass is given as 7.3 10 raised to the power minus 4 kgs. We need to convert it into grams. So convert it into 10 raised to the power 3. So we convert this into grams. Sorry. Avogadro's constant 6.02 10 raised to the power 23 divided by the number of particles, that was 4 10 raised to the power 22. So let's calculate this. 7.3 times by 6.02 divided by 4 times by 10 raised to the power minus 4 plus 3 plus 23 divided by 22, we get 12.198. So that means we need the mass number. Obviously, that's going to be an integer, so 12. Sorry. I just realized I accidentally wrote divided by instead of minus. So this is 10.9. So 10.98, so roughly equal to 11. That's it. All right. Moving on to the next question. State what is meant by luminosity of a star. So we can also see that over here it's the total power radiated by the star. So you can also say that in terms of energy per unit time. So sorry, luminosity. Luminosity is the total energy emitted by a star per unit time. That's it. So total energy emitted by the star per unit time. That's it. Explain how a standard candle in a distant galaxy can be used to determine the distance of the galaxy from an observer. This is also easy and also covered over here. So if you see this over here using the standard candle, okay, this one, standard candle's luminosity, we already, like, that's why we call it standard candle. By measuring its observed radiant flux intensity, and applying the inverse square law, the distance d to the galaxy can be calculated or estimated. So that's exactly what we just have to write. So uh, standard candles or standard candle has known luminosity L by measuring its radiant flux intensity F and applying inverse square law F is equal to L over 4 pi d squared. The distance d to the galaxy can be determined. So this is like obviously an estimate over here because this assumes the ideal scenario, but for our purposes, it's fine over here. Okay. Sun has a radius of 6.9610 raised to power 8 meters and a surface temperature of 5780 Kelvin. The light from the sun is observed to have a peak intensity of at a wavelength of 501 nanometers. So what we can do over here is use the Stefan-Boltzmann law. So according to Stefan-Boltzmann law, luminosity is equal to 4 pi sigma, which is the Stefan-Boltzmann constant, r squared t raised to power 4. So 4 pi, Stefan Boltzmann constant, we need the value. So we go to the data booklet. Oh, sorry. 5.67, 10 raised to the power minus 8. 5.67, 10 raised to the power minus 8. R raised to power 4, so radius is given as 6.96, 10 raised to power 8. And temperature is, sorry, this is squared. And 5780 raised to power 4. So we calculate this now. So 4 pi times by 5.67 times by 6.96 squared, oh sorry, squared. And then we have 5780 raised to power, sorry, I don't know what's going on, raised to power 4. Now the powers of 10 are minus 8 plus 16 because 8 raised to power 8 raised to power 2. And that's it. So you have 3.852, 10 raised to power 26. So this is 3.8. Now we need to see how many significant figures we have. So 3 significant figures over here, 3 significant figures. So we can't leave it as 3.8. It's more appropriate to leave it as 3.85, 10 raised to power 26 watt. Another star emits radiation that has a peak intensity at a wavelength of 624 nanometers. Determine the surface temperature of the star. Okay, so we know that from the Wien's displacement law, that lambda max times by T is equal to constant. Since we don't have access to this value, we can use it as a proportionality. So lambda 2 T2 is equal to lambda 1 T1. So we need the surface temperature, so T2, that would be lambda 1 T1 divided by lambda 2. So lambda 1 was 501. Temperature was 5780. Now the second wavelength is 624. So 501 times by 5780 divided by 624, we get 464067. So again, we just need to leave it at 3 significant figures, so 4640 Kelvin. And that's the end of this paper. So if you learned something, if you enjoyed this, please comment, like the video, and subscribe to our channel. If you feel that I was unable to explain something good enough, please reach out in the comments. I will try again. If you think I made a mistake somewhere, please also comment, reach out to us. If you feel your preparation is unsatisfactory for the upcoming 16th May exam, reach out to us through our link tree. The WhatsApp number is given. You can reach out to us. The email from the YouTube information you can find out. From the Instagram, from the Facebook, you can reach out to us. I will definitely be glad to help you out with some last minute revision. And if you are watching this video at a later date and you want to study physics or math, you can contact us for the tutoring also. All right, so see you in the next video. Bye-bye.